Hello from Brigham Young University. I am Norm Jones, and today we are going to talk about the governing differential equations that are used in simulating the flow of groundwater through aquifers. And we've built up the background we need now by reviewing hydraulic head and Darcy's law and layered systems, multiple dimensions. Now we're ready to go ahead and derive the full set of governing equations that we'll be solving for the rest of the semester using our computer models. So background, we have been solving problems using Darcy's law and through homogeneous systems and layered systems, but these were all simple one-dimensional problems where it was possible just to directly apply Darcy's law. But in a real-world situation, the geometry of the aquifer and the properties are more complex, and therefore we need a more broad and expansive, a more general set of governing equations, or governing equation. And so we're going to derive the general form of our three-dimensional governing equation, and then we're going to come back later and do some variations on that. So, what are our critical assumptions? First of all, we are assuming that the soil is saturated, meaning that the equation that we're going to derive is used to describe flow in the saturated portion of the aquifer, not in the partially saturated zone. There actually are equations out there for simulating flow in a partially saturated environment. But typically, that's just a fringe on the edge of our aquifer, and it doesn't really make that much of a difference. So primarily, we just model flow in the saturated zone. We're also going to assume Darcy's law is valid. That's a critical part of this derivation. And another critical assumption is that mass is conserved. What goes in must come out or be stored based on a conservation of mass. Specifically, this is kind of the general form of the governing equation. And if you look at a subset or a section of the aquifer, a representative volume of the aquifer, if you take the water going into that volume minus the water going out, any difference would be on account of a change in storage or input or output from sources and sinks. So a change in storage means maybe that remember we're talking about a saturated zone, so that could either expand or contract a little bit, changing how much water is stored in that element. Or sources and sinks, maybe in this representative element you have a well screen, you're pumping water out. Well, that would cause a difference in the inflow versus the outflow. Or maybe there's a spring or a stream or something, and so that's what we mean by sources and sinks. So there has to be a balanced flow system that we account for, and this is actually, as you will see, a very important part of our derivation. So we are first going to consider a special case where we have steady state conditions. So that means that we have long-term average conditions, and the stresses or the inputs, the boundary conditions on our aquifer do not change. We're also going to assume, just for the time being, that we have no sources and sinks. We'll add that back later. And therefore, the two terms on the right are set to 0, and we are left with just this very simple inflow minus outflow equals 0. So that's our mass balance assumption. Okay, so this cube is what we call our representative element, and it has a volume of dx, or the dimensions of dx, dy, and dz. And we are going to look at something called the mass flow rate, which is the density of the fluid, the water, multiplied by the velocity. This is actually Darcy velocity, but taken together, the density times the velocity is basically the mass flow. And first we're going to look at the mass flow in the x direction. And so as you see on the left side of that cube, we have the mass flow in the x direction. And on the right side, we say the mass flow out is equal to the mass flow in plus the derivative in the x direction of the mass flux, the mass flow, times dx. So that derivative is basically how that mass flow is changing in that direction, multiplied by that length. So a simple way to think of that is whatever comes out the right side in the x direction is whatever came in the right side plus however much the flow rate has changed as it travels from the left to the right. That's how you describe that equation in a more general sense. So one question you might be thinking is, why would the mass flow change? Put very simply, some of the water that comes in the left side may be diverted up or down or in the y direction and go out one of the other faces. So that's a simple way of thinking about that change. So if we go back to our inflow minus outflow equals 0, and if we look at the inflow minus the outflow in the x direction, so we take the mass flow in is rho vxn, and if we subtract from that the mass flow out, which is the mass flow in plus that derivative. Now remember, if we're looking at let's see, we're looking at this, let me turn on my labeler. So this is the mass flow out. So if we take the mass flow in minus the mass flow out, we get this expression here. And furthermore, we're going to multiply that by dy dz. So now we're looking at a flux. So we're taking the mass flow rate in the x direction, and we're multiplying it by the area that it's flowing through. Well, that cross-sectional area, if you're going in the x direction, is dy times dz. It's the area of this face right here. And so that's why we're multiplying by dy dz right here. Now, if you look at this, the rho vxn minus rho vxn, those are going to cancel. And so we can then go to the next part here. And so we're just left with this derivative, the derivative of the mass flux in the x direction minus the derivative times, now we have dx times dy times dz. And if we repeat this in the y and in the y direction, we get something very similar. All the same principles apply. We end up canceling these two terms. The dy is multiplied by the dx and the dz, and we end up with this expression here, which is very similar, but it's the derivative in the y direction of the flow in the y direction, the mass flow in the y direction. And then again, we do the same thing for z. And then what we do is if we look at the total mass balance for that entire volume, we have to add up the inflow minus outflow sums or differences for the x, y, and z. Those all have to add up to 0, meaning that if there's any difference, if there's any water that came in the x direction that didn't go out the x direction, it's going to have to be balanced somehow in the y and the z direction. So in the end, the total amount of water or mass flow going into that volume is completely balanced by the mass flow going out. So if we then take those three terms that we derived and put them together and set that equal to 0, now we can start simplifying things. If you pull out the dx, dy, dz, and if you divide both sides by dx, dy, dz, and then divide both sides by -1, we end up with this really simple expression here. The derivative of the mass flow in each direction, these rates of change, if you will, they all have to balance. So this is kind of, if you think about it, it should make sense a little bit intuitively. Whatever change there is in the x direction has to be balanced by a change in the y and the z direction, and vice versa. And so those all kind of have to add up to be 0. And so, but we can make a further simplification. You may recall from calculus that if you're taking the derivative of an expression such as rho vx, the rho part is a constant, so you can pull it outside the derivative. So I don't have it written here, but you could replace this with the density times del Vx dx plus the density times del Vy del y and so forth. But then if you just divide by the density, you can get rid of that term. So assuming that the fluid density is a constant, we can pull it out of the derivative, and now we're simply left with the first derivative of the velocity in the x direction plus the derivative in the y direction plus the derivative in the z direction equals 0. Okay, now remember this Vx, Vy, and Vz, this is the Darcy velocity. Therefore, we can go back to Darcy's law, and we're working in 3 dimensions now, so we have to use the 3-dimensional version of Darcy's law. And if we remember how to do a matrix multiplication, Vx is equal to minus kxx times del h del x minus kxy times del h del y minus kxz times del h del z. And so, so essentially this, let me draw this here. So this expression right here is basically Vx. And so what we're doing is we're substituting that's this part of the equation, and so we have to take the derivative of that. And so if we take that derivative, we end up with this expression shown here. So it's minus kxx times the second derivative of h with respect to x, but minus kxy times del squared h del x del y minus this kxz times del squared h del x del z. And if we do that for Vx, Vy, and Vz, and if we add all these terms together into that equation, we end up with this beautiful, complicated equation here. But remember that kxy is equal to kyx, and kxz is equal to kzx, and kyz is equal to kzy. Therefore, we can combine those terms, and this becomes our full equation for the general case in 3 dimensions. And remember, since we have the kxy, kxz, kyz, that means our off-diagonal terms are non-zero. But if we remember back to our previous lecture on Darcy's law in multiple dimensions, if x, y, and z correspond to the principal axes of permeability, then the off-diagonal terms go to 0. And we are left with this expression, much simpler. So those last three terms up here in this first equation, this one, and this one go away. And we're left with this simple equation. And this is more commonly written. At this point, we typically get rid of that double subscript and just write it in this form: kx times the second derivative of head in the x direction plus ky times second derivative of head in the y direction plus kz times the second derivative of head in the z direction. That is basically, the same thing we had here at the top, except we've gotten rid of those off-diagonal terms based on this assumption on the principal axis of permeability. Furthermore, if kx equals ky equals kz, in other words, if this is isotropic, the hydraulic conductivities are the same in each direction. Now, this very rarely happens in nature. It almost always, ky or kx and ky could be the same, but kz in the vertical direction is typically a fraction of the hydraulic conductivity in the horizontal direction. But if you make that assumption, then the subscripts go away, and we're just left with k, and you can divide both sides by k. And we have this form of the governing equation, which is sometimes called the Laplace equation. You actually may have encountered this when you're learning about seepage in an introductory case. We often solve a version of this when we solve flow nets. We make that simplifying assumption. Now, for all of these equations, whether it's the general case or the or this case here with the off-diagonal term 0, or even the Laplace equation, these are all differential equations. And if you've had a course in differential equations, you probably remember that the solution to a differential equation is a function. In this case, the dependent variable is head, and so the solution to these equations is a function describing head in terms of x, y, and z. So if we have a solution, then we can plug in any location in the aquifer, and it'll tell us the total head. So that's ultimately what we want to know, is how does the head vary through our aquifer based on the material properties, the hydraulic conductivity, the geometry, the sources and sinks, which we'll get to in a minute. But that's ultimately what we're going to solve for. So in order to solve a differential equation and to come up with this solution describing how the head varies, we have to define some boundary conditions. And that's, if you've had differential equations, you know that defining a sufficient number of boundary conditions is the only way you can solve these equations. And so no matter how we go about solving these, we have to come up with some boundary conditions. So let's talk about what do boundary conditions mean in the context of groundwater modeling. So here's a cross-section through a site, and we have, what do we have here? We have recharge coming in, rainfall comes down. It's not illustrated here, but you would have recharge coming in. So that would be an inflow. And the flow, we have a stream in the middle. So the recharge that's coming into the system would eventually be flowing towards the stream. So this stream would also be a boundary condition. It's something, the water level is fixed at that stream. So that's a boundary condition. And then, let me change colors a little bit. So this entire boundary, it kind of blends in there, that I'm tracing along this side. This is what we call a no-flow boundary. We have an impermeable layer underneath this system, and so that would be, if we say water cannot pass through the bottom, that's a type of boundary condition as well. So let's go to the next slide here. So here's one that we're actually going to solve later in the semester. This is a site in East Texas, South Central USA, where there's a site in a valley with some alluvial fill. There's a proposed landfill, and we're building a groundwater model in preparation to determining the impact for that. And so in this case, the let's see, let me change my highlight color a little bit. Let's go to a pink. So we have a number of things. First of all, right along the bottom here, this is a river. And that river acts as a boundary condition. And we have a river or a stream going up this other side as well. So those two, that represents what we call a head-dependent boundary condition. And let's see, let me go back here to a different color. And then, you know, this boundary up top, this is where the alluvial fill in the valley pinches out, and we have some limestone bedrock outcropping there. So this is a no-flow boundary condition. And then some other things, these blue lines in the middle, these are drains. So these are ravines that if the water table gets high enough, it drains out. But if the water table is low enough, it doesn't have any impact. So those are basically external sources and sinks. And then we have a couple of wells here. We also have recharge. All these things taken together provide the boundary conditions that fix the mathematics so that we can then solve this, the differential equation, the governing equation. And, you know, what do we mean by solve it when we're done? Well, first of all, so this is kind of a conceptual model rendering. We then convert that to a numerical model. This is a mod flow computational grid. And essentially, we then solve that governing equation for each of these cells in the grid. And then these little colored dots represent the actual application of boundary conditions to those cells. And then we run it through a solver, and it ensures that at each of these cells, if you look at the head at each cell in relation to the other cells around it, that governing equation is satisfied. And once we do that, we end up with a solution, which is shown here. These blue lines are contours of total head found by solving that governing equation after the application of the boundary conditions and also the material properties, the hydraulic conductivity of the aquifer, the thickness of the aquifer. All those things are taken together, and this is the solution of our governing equation. Now, once we know how the water table or the head varies throughout our aquifer, we can use this as a predictive tool. We can show how it will respond based on certain changing assumptions. We can determine how long it takes for water to travel from one point to another point. In this case, as you will see, we had a landfill up here somewhere, and one of the questions you can answer with this is, given that location of the landfill, if you had a leak in your landfill, where would the water go? Would it go down here to the river, or would some of the water end up going over here into the well? Those are exactly the types of questions that we can answer once we have this solution. And so this is a nice little model to explore some of these ideas behind groundwater modeling. Okay, so how do we solve this? How do we solve our governing equation? For really simple cases, if you have very simple geometry and very simple boundary conditions, you can use what is called an analytical solution. You can actually derive an equation. an algebraic equation with different coefficients to solve for the distribution of head. Typically, we can only do this in special cases with one-dimensional flow. We aren't really going to explore that in this case. Oh, another example of this would be well equations, which you may have been introduced to in a hydrology class or a geotechnical engineering class or hydrogeology class. But for more general cases, you could theoretically use a graphical solution like a flow net. Those are rarely used anymore. The most common solution is to use a numerical solution. Typically a finite difference or finite volume solution or finite element. And again, I just illustrated for you a numerical grid. For each of these numerical solutions, typically you subdivide or discretize the aquifer geometry into a series of small cells or elements, and then you look at each cell and compare it to its neighboring cells, and you make sure there's a way to force the governing equation to be satisfied over in that small scale case. And that's the kind of solution we're going to use this semester. I'm not going to, in this class, we're not going to really dive into the whole formulation and solution of the finite difference equations. You can look that up for the mod flow model if you want. But we're going to get a lot of practice actually building numerical models. But you just need to understand the whole point of this is to solve that governing equation. And you have to have, it is possible to build a numerical model where you don't provide sufficient boundary conditions and it blows up. So we're going to discuss boundary conditions in pretty good detail, and we're going to talk about the different solvers that are used in ModFlow. There are different algorithms for solving these equations that you kind of need to know something about in order to use it. So let's go back. Earlier in this presentation, I gave you the full mass balance equation, and we set the right side equal to 0, saying we're going to ignore sources and sinks and transient terms. Now let's add those back in. So first of all, if we just look at sources and sinks, again, suppose you have like a well inside your representative element. Well, then you have to, in order to have a mass balance, you have to account for that on the right-hand side. So inflow minus outflow is not going to be 0. It's going to be whatever the change is resulting from these sources and sinks. Now, a source is something that puts water into the element. A sink is something that takes water out. So again, if you think of a well, the well could either be an extraction well or an injection well. Now, it turns out that this is a really simple change to our equation. We just add an extra term on the right, which is minus r, which is basically the change in flow resulting from sources and sinks. And so, sometimes I've seen that positive or negative, but anyway, that's all we have to do to account for sources and sinks. And then finally, if we're doing a transient model, meaning the sources and the stresses, the pumping rate, the recharge, and other things change over time, now we have to do what's called a transient model, and we have to introduce another term back into the system, and that's this storage term. And what that means is over a certain period of time, as things are happening inside our representative element, the amount of water stored in the pore space in that element could theoretically change over time. Why would it change? Based on the pore pressures and the stresses on the soil, that aquifer matrix could expand or contract, and so as it expands, water comes into storage. As it contracts, water goes out of storage, and so this term right here represents that change in mass as a result of these transient changes. So by accounting for that, we can add this term right here. It's everything we had before, but we've thrown in this term where S sub S is something we call specific storage. And we have this derivative del H del T, the rate of change of the head with respect to time. So actually there are a number of assumptions that go into play into deriving this particular term. Specific storage times the head derivative with respect to time. And we're actually going, later in the semester, we're going to revisit this and we're going to go through the derivation of that term. So don't worry about it for now. For the time being, we're only going to look at steady state models, but down the road, we're going to take a look at that. So this is, what's in front of us right here is the governing equation that's used in ModFlow. And you'll notice that there are no off-diagonal terms. So one of the assumptions in ModFlow is that your X, Y, and Z axes are aligned with the principal axes of hydraulic conductivity. And the benefit of that is it keeps our governing equation fairly simple. So that concludes our derivation of the most general form of the governing equation. In our next lecture, we're going to show you a variant of this for two-dimensional flow. And as I mentioned, later in the semester, we're going to add this transient term. But we have the tools now to begin solving this problem. Thank you.